Werkt niet. Nou, is goed. Geen probleem. Nee, doe het niet. Nee. Dat lukt niet. Bedankt. Okay, so what we'll do today is two applications of lubrication theory. So last Friday we simplified Navier-Stokes equation in the case of in the lubrication approximation. Lubrication approximation is an approximation when you have a thin film of fluid. So you have a larger length scale in the flow direction and a shorter length scale across the flow direction. And we assume that in these cases the effect of inertia can be neglected or negligible. And this is a case if the Reynolds number based on the thickness height times h divided by L is a small number. And this is this is what we came to. And those are the simplification of Navier-Stokes equation for the lubrication approximation. And so we'll do two examples. The first example is a slider bearing or an air bearing. Oh, hold on. Before I do this, I just wanted to also make a note here. So when you'll be in the context of lubrication, theory, usually, so as always, you always have to make a statement, usually, in most cases, to solve a problem, get the velocity field or the pressure field or anything, you probably have to say something about conservation of mass, and you have to make a statement about Newton's second law. So write some form of the momentum equation, integral form, Navier-Stokes, Bernoulli. You always have to do both. In the case of lubrication, when you've determined that the assumption of the lubrication assumption are valid, then in most cases, not always, but you want to use the continuity equation for mass conservation. You will want to use the equation we discussed at the very beginning of the class. So we derived mass conservation, and then I think it was the 20th something of September, either on a Tuesday or on a Thursday. So I think 21st. You go back to your note. We derived an equation which replaced the continuity equation, so mass conservation equation for a lubrication layer, and that equation was partial H over partial T plus partial Q over partial X is equal to 0. And I said, remember this because you'll see it at the very end of the class. So if you don't remember, just go back to the notes. I think it is somewhere, it is on a Tuesday or a Thursday, 20th something of September. So in that case, H, let me just really briefly remind you the notation setting. H is the height of the film. So that would be here H as a function of X and time. And Q was the volumetric flow rate at any given value X. So that would be the volumetric flow rate, also a function of X and time. And Q would be the integral from 0 to H of essentially U dy, right? This U here is U dot N, where N is a normal pointing in the X direction, okay? Does anyone remember that? Vaguely? Yes? Okay, great. I see at least one person that remembers it. I emphasize that. If you don't remember where it comes from, go back to your notes. We derived that equation in two ways. One with a control volume approach, and the other way by directly integrating the continuity equation. If you remember that, we did both cases. So in most cases, again, when you have to write the continuity equation, those derivations would be good to have on your cheat sheet. In the case of lubrication, you may want to use that equation directly. Of course, if I ask you to derive it, then you have to be able to derive it however you want. But you have to be able to get to that point, or if I say directly use this, then you can directly use this. And in most cases, it's a very useful equation to have. Okay, so that being said, now we will do the air bearing. So an air bearing looks like this. Looks like this. It's not a real industrial air bearing. This is a lab demonstration, but this represents a top, the heavy load. This is heavy. In principle, you have something on top of that, and so if I turn it here, not much happens. It is quite heavy, so there's a lot of friction. If I turn it in the other direction, and this is going to rotate for a long time. And now there is just air. Right? It's a very, you don't see it, but there's a tiny gap. You don't see any gap between the top part and the bottom part. Right? And actually right now they're touching, but when I start rotating it, and there's a little cushion of air. And if you remember correctly, we scaled the pressure, and the pressure scales with 1 over h squared. So if h is small, you get significant pressure. And so you create enough pressure in the air to sustain that rotation for a while. Okay, so we'll try to deduce that and see, exactly, this is a typical application for lubrication theory. Right. So here, what you don't see is not the surface. The bottom surface is not completely flat. You see those little things here. You see these? So those are just little grooves. They are very, I can't tell you how high they are, but they're probably on the order of tens of microns, probably less than 100 micron. I would say 10 micron or something. Such that, so this here is a little groove. So here, this is a bit, this sticks out a bit. Right? So you essentially just etched a bit here. So you have little patterns on the surface. You see that? Okay. So, and those are periodic. Right? So you have, if I'm thinking about the height of the film, right? The height here is going to be lower, and then here higher, lower, higher, lower, higher, lower, higher. Okay? So I'll show you. Just distract you by doing this again. It's quite fun. So in the break, you're welcome to play with that. But so essentially, if say I'm not going to keep this circular geometry, I'm just going to slice this open and then stretch it like that. Okay. So we'll have just a linear repeat of this surface topography. So on the top plate, what we can say. So we have the bottom plate. This is solid. Right, so this is what we're going to model. We have the bottom plate, which is solid. And on the top plate, we have something like that. So this is where we etched a little bit. And then, of course, here I'm just separating those such that the analysis will be easier for me. And here I'm making those patterns. Actually, they don't really look like that. The pattern, they're much more slender, a bit more like that. Right. I mean, I could have just many of these, but we'll just investigate one isolated one. But we have a repeat of those sort of little patterns. Okay. And what I want is I'll just isolate one. So we'll just take one of these and analyze one independently. And this is my top surface. I have little dents. Do you understand the geometry? Yeah? And so it's just been cut and stretched, and we just reproduce it to infinity. So that's what we have. And then we have the top plate, in that case, which is moving with a linear velocity u compared to the bottom plate. Okay? And what we want to characterize is, if this is moving at a velocity u on top of the plate, what is the force normal to the bottom plate? What is the force which is going to push the plate up? This is essentially what we want to characterize here. See, it's still turning, so it's been turning for a while. Right? So you notice here that in principle, if you do also a ratio of the normal force to the tangential force, you expect the normal force to be much larger than the tangential force. Right? There is some friction, but you see this thing can rotate for a long time. So, okay, so here we have to introduce annotations. So this is the topography, and I'll just reproduce it here with the notation that we will use. So let's look at one of these little elements. Okay, and we'll be in the lubrication approximation. So this here will be my length scale L, capital L. So here I'm at x equals 0. And here I'm at x equals capital L. Okay, now let's assume that this plate is hovering at a height h0 above the bottom plate. And we'll call h1 the height here. Well, we don't really know what h0 is in principle. We'll discuss that later on, what fixes h0. But we do know the geometry because we did the groove. We machined them. So assuming we have good precision, we roughly know what h0 minus what h1 minus h0 is, such that we will write the film thickness So here, of course, the film thickness is sort of set by your problem. In some cases, h is what is unknown, right? If you're thinking about, we'll do later on paint, right? If you have paint which you just painted on top of your surface, how h changes is what is unknown. In that case, how h changes is what you impose, because you impose the top surface. You impose the topography of the top surface, right? So depending on which problems you have, you're interested in different things. Here you impose those grooves. You impose the flow to go through that particular geometry, and what you're interested in is the force. In some cases, what you're interested in is the film shape. If you have a free flow, or if you have any kind of thin film covering or coating, for these applications, then you might be interested in the film shape. However, here the film thickness is sort of imposed, so you can write it. So h as a function of x, I'll put t for now, right? And let's assume that we are t equals 0, is going to be equal to h0 plus alpha x. We assume we have a linear profile, and in that case, alpha is what is known. Alpha is h1 minus h0 divided by L. Right, so alpha characterizes the slope of this pattern. Yeah, is that clear? Okay. So this is what we have. Now, as usual, we'll assume that we have a fluid of viscosity mu. What is our fluid here? Air. Right? It's clear. There's no oil. There's nothing. This is our fluid here is air. Okay, and then the first question would be, right? The problem is paused in this way. You don't know exactly in which frame of reference to be, and in principle, and now the whole thing is set in motion because the top plate is moving at a velocity u, right? So when I write it this way, it seems like I am in the reference frame attached to the lab, to the bottom surface. Yeah. Now, do you think this is the best reference frames in which to be? So the answer is no. You actually would want to pick another frame of reference. Does anyone see why you would pick it? Why you would want to pick another frame of reference? And which one would it be? Yes, you want to actually be on the reference frame here of the top plate. Yeah, do you see why? There's no. Well, I've stretched everything anyway. Right? I cut it and then I open it like this, so there is no rotation. So right, I have sort of a line of those little grooves, and this thing is just moving linearly. This is the problem I'm solving. And physically, it's going to be similar to this. Of course, there are some differences, but physically, it's going to be similar. But why do you not want to be in the frame attached to the bottom surface? Huh? Because of? Exactly. Yes. I mean, so the point is, if you're in the frame of reference attached to the bottom surface, then you have this object that moves through your lab, right? So you have to impose a boundary condition on a moving object. So this is going to be very unsteady, right? This is going to be an unsteady flow. You're going to have to solve for everything is going to be unsteady in that frame of reference. As opposed to if you put yourself in the frame of reference attached to the top part, then of course the bottom part moves, but the bottom part doesn't have any geometrical structures. So it doesn't really matter. The shape of your boundary the shape of your groove doesn't change. Right? And there you can make use actually, then you will see that the equations are actually steady. You can assume you have a steady boundary condition on the bottom surface and a steady no slip. So you have a steady no slip on the bottom surface, which is u equals to u minus u. Right? And then you have a steady no slip boundary condition on the top surface, which will be that the velocity is equal to 0. Right? Those can be easily matched. But if you are in the frame of reference attached to the bottom surface, then you're stuck with a boundary which is moving. Right? And that's complicated because then everything is unsteady, of course. Do you see that? That's always a question which you may want to ask yourself. If you find that you have to impose a boundary condition on something which is moving, sometimes it can be really tricky. Right? So doing a change of reference that allows you to reuse all of the equations, right, on the boundary which is fixed in time. If you have this opportunity, then do this. That's the first step. Now, the other thing is, if you do that, now you're in a frame which is translating with respect to the lab frame. The lab frame we know is inertial. What do you need to be able to assume to do that and still use all the equations we've derived? Velocity is constant. Yeah? If the velocity was not constant, so if you were accelerating, then now you're in a reference frame which is translating, okay, but you are in a non-inertial frame of reference because it's not moving with a constant velocity with respect to your inertial frame of reference. In that case, for a long time, if we just do a quick analysis, right now everything is steady. The velocity is slightly decreasing, but it's barely noticeable. You cannot notice really. So for a few seconds, if you're doing this analysis, you want to know what the pressure is. But right now, you can assume you have a steady state. The top velocity is constant, right? And therefore, you can be in the frame of reference moving with the top surface. And you can assume safely that the velocity is constant in time, and therefore that you are also in an inertial frame of reference. Yeah. Now, of course, here this is not true because this thing is rotating. Yeah. But I'm talking about that. Yeah. Is that okay? Okay. So, number one, we'll put ourselves, so choose frame of reference, moving with the top surface. Okay? So really what we have then is that this guy is not moving, but the bottom plate here is moving at a velocity minus u. Yeah? Do we agree? If we're in the frame of reference not moving and we are on the top surface, then this is what it is. So this is the first question would be to choose the frame of reference. We want to be in the top frame of reference. Okay, and then if we want to get to the pressure, we know we have to say something about mass conservation. We know we have to use the momentum equation somehow. Now let's start with mass conservation. Okay, so from mass conservation, and I'm going to write mass conservation in the typical lubrication way. So we have partial H over partial T plus partial Q over partial X is equal to 0. Now, in the frame of reference that we have, what simplification can we do? The first term is 0. In that case, then H is going to be non-dependent on time. So here we have a steady state. This is because of our frame of reference. So our equation reduces to partial Q over partial X is equal to 0, which means that Q is essentially a constant. Right? It's independent of X. Now, is that surprising? Who is surprised by that? We're not surprised, huh? We're still assuming the flow is incompressible, and now we just have the flow that is squeezed through a little channel. And so this is the same kind of mass conservation that you use in your bachelor's. The fact that your volumetric flow rate at any given cross-section is constant because of mass conservation and incompressibility. Yeah? So, I mean, you should always be, you see this, Q is equal to a constant. Is that surprising? No, of course not. You could have directly written in that frame of reference that Q was equal to a constant. The same kind of mass conservation statement that you've been doing for many years. Yeah? So, let me call this constant Q naught. Okay, so we know that the volumetric flow rate is a constant. Okay, so this is probably the most information we can extract from the mass conservation equation. And so what do we have? What do we have left? So we have the Y momentum equation. Given that we have air, what do you think about the body forces? Are these going to be important or not? No. And do you think actually the mass of the air is what is driving the flow? No. Right? So in that case, it's actually very fair. You can keep it and then do a dimensional analysis. That's fine. You'll find that it's not the hydrostatic pressure, but the aerostatic pressure difference, over a small gap. So the rho GH is very small, and it's extremely small compared to the sort of pressure we will generate in that gap. So then you can neglect it. But in principle, just common sense tells you that you can neglect that. So you have mass conservation. Now let's use the Y momentum equation. So we have partial P over partial Y is equal to 0, which tells you that P is only a function of X. Yeah. And is it a function of time? No. Because everything is steady in that frame of reference. So in the other frame of reference, P would be a function of T, but in the frame of reference attached to the top plate, then we don't expect P to be a function of T. So here, P is really just a function of X, and this is also because of our frame of reference. We are steady in that frame of reference. Okay. So P is only a function of X. And then the last equation that we have is the X momentum equation. Minus partial P over partial X plus mu times the second partial of U with respect to Y plus the body forces in X equals to 0. Now what are the body forces in the X direction? There is nothing. In that case, there is no gravity in the X direction, so this one we can directly cross out. And so this is, this looks, of course, like the equation we've had when we neglected inertia. So unidirectional flow, we had the same equation, and so in that case there, you have a little hope of integrating the equation. And this is sort of a template for lubrication or for unidirectional flows or any of that. In that case, you just have P. This here is only a function of X. It's not a function of Y. Right? And therefore, you can actually integrate by keeping X constant in Y. Do you see that? So I think this is one of the only cases where you will actually directly try to integrate the Navier-Stokes equation. So when you and so recognize that when you are in the framework of lubrication equation, that will often be the case. You will be able to integrate at a constant X your X momentum equation, and you should get something which looks like a parabolic profile. This looks exactly. You will have a pressure gradient, and so this is going to be Poiseuille-like. It's going to always be like a mix of Poiseuille and Couette. So it's a unidirectional flow. Part of it could be just shear, so you could have just a Couette flow. In that case, you expect that the top surface, if H1 was equal to H0, it will be exactly Couette. So you might have some component of Couette in there, but you also have a pressure gradient, right? Because you want to create pressure underneath, right? And so you might have also a component of Poiseuille flow. Right? But in general, when you are doing lubrication, you'll be able to integrate at a constant X. So here, let me write this: partial P over partial X is only a function of X. It's not a function of y, so we can integrate at a constant value of x. We can integrate that. So if we integrate it once, we get that. So let me just rewrite that. I have second partial of u with respect to y is equal to 1 over mu partial p over partial x. So here I just rewrote. So if I integrate once at a constant x, I get that partial u over partial y is equal to 1 over mu partial p over partial x times y plus a constant. Yeah. And when I integrate a second time, I get that u as a function of x and y is equal to 1/2 of mu partial p over partial x y squared plus, let me call it a constant 1 times y plus a constant 2. Right? Those constants might depend on x. Yeah? So if this term is 0, we have a Quetelet-like flow, and this is your Poiseuille-like term. Yeah? Now what boundary, so we just integrated, what are our boundary conditions? We have to integrate, we need boundary conditions to identify the constant. We have 2, which one are they? Yes? Huh? At the lower surface, yes, so at y is equal to 0, we have that u is equal to minus capital U, and at y is equal to h of x, right? U is equal to 0. Is that clear? Those are our boundary conditions. So with that, you can identify the constants. I'm not going to do it here. I have the solution written in there. So we have that. So with this, we get that u as a function of x and y is equal to minus 1 over 2 mu. So here, so today I'm not going to do the integrals and everything. Yeah? So I'll leave them to you. Those are not difficult, but it's very easy to make mistakes. Okay, so just practice that a bit. But I won't do it here. I have derived everything beforehand because otherwise I know it's going to be a mess. So partial p over partial x times y times h of x minus y minus u times h of x minus y divided by h of x. Okay, the first thing we want to do is to check that all our terms are dimensional. Right, so this term has the right dimension. It has the same dimension as this one, so we know it's fine. And this term is a velocity times a length scale divided by a length scale, so it's a velocity. So this is okay. And then we check that at y equals 0. So when y is equal to 0, this whole term is equal to 0. Right? And this term here will be equal to minus u times h divided by h, so minus u. So this is fine. And then we check that at h, at y is equal to h, we have u equals 0. So at y is equal to h, this term here is equal to 0. So this whole term here is equal to 0. And that term here is also equal to 0. So the velocity is equal to 0. Yeah? Yes? So you see here that my two constants did depend on x. Let me just rewrite it here to make it clear. This is a constant, of course, which depends on x. Right? And it depends on x through h. Okay, so this is our velocity profile. Now there are a few things that we still don't know. We know the shape of our velocity profile. What do we not know? It's not like we've solved the whole problem. What do we not know? Always keep track mentally of what you know and what you don't know. You know what the shape is. It's going to look like partly, part of it is going to be a couette. It's a couette plus a poisette. So it's going to be parabolic, a parabola-looking flow. But what do we not know? So we don't know the h naught in the h. Right? In the h of x, we don't know the h naught. That's true. We sort of gave it a name. It's h naught. That's the height at which the top surface is from the bottom surface. But there's something else we don't know, and that is dp over dx. That's what we're interested in. Once we have the pressure distribution, we can integrate and get the force. And so here we still, we still don't have everything. The only thing that we know is that dp dx is only a function of x, which is why we were able to integrate at a constant x. So always know why you can do that. Again, I'm going to repeat this, but I want to really put the emphasis on that. The only reason why we were able, in that particular case, to integrate is because dp dx is independent on y. Therefore, you can integrate and you can get this easy form. You just, if this is a constant at a constant x, then when I integrate, I just have a y in front. But usually, this is never the case. Yeah. Okay. So remember, we're still after the pressure. So we want to know the pressure. So we have to combine all of our statements, right? And in particular, what do we know? We know that that we have to conserve mass. Yeah. We have to conserve mass. So we know that actually, as a function of, once we integrate u over y, we're going to have a constant which is going to be the volumetric flow rate. Okay, so let's do that. So then we combine the two information, because if you want, the pressure comes from the fact that we are going to squeeze. If you look at this picture, it's always good to have some physical intuition about that. When this plate here moves, you're trying to squeeze air through that little gap, and it's that squeezing which is going to, we said like the pressure is what develops in the flow when you're trying to change the volume, right? So it's this squeezing that is going to generate the pressure, right? And the squeezing comes, of course, because you have to conserve mass. So before you've combined the two, it's the squeezing due to the mass conservation which will determine how much pressure you develop underneath inside of your gap. So we need to combine the two statements. Okay, so let's write this. So Q0, that will identify Q0, is equal to the integral from 0 to h is a function of x, of u dot x dy, and u dot x dy is just the u component of the velocity. H of u dy, right? So we're holding x constant here. So I won't do this integral. I have the answer written out here. So this integral here is equal to, so when you do this integral, you will find, this is just a second order polynomial in y, so integrating this is not, it's not, you know how to do that, right? The y squared term gives you a y cubed divided by 3, and the y term gives you a y squared divided by 2, and then you just integrate. So when you've done that, you get minus h cubed divided by 12 mu partial p over partial x minus u h minus uh. Okay, so we know that this here is a constant, and so we can express a lot of things. So let me just write that here. Q naught, which is a constant, is equal to minus h cubed divided by 12 mu partial p partial x minus u times h. H here is always a function of x. This is the height of our film. Okay? So with that, now even though we don't know what h naught is, from this equation you see that we know what dp dx is, for a given h naught, which is not fixed now. Right? The only thing is that the constant q naught is not really determined. We don't know how much flow goes underneath, and that is a function, of course, of how fast the top plate, goes, and is also a function of h naught. So let me rewrite dp dx. So then dp dx, which is what we are interested in. We want to know what the pressure distribution is underneath. So dp dx is going to be equal to, I'm just going to reform that, minus 6 mu u, I'm just inverting the formula, divided by h squared, function of x, minus 12 mu q naught divided by h cubed, function of x. Okay. Now I'm not going to do the integral again. So this is from here to here. You have to do it. This is one integration step you have to do. This is just inverting. This is easy. And now to get to p, you need to also integrate. And so if you want to know p at x, right, minus p at x equals 0, which is what we might know, right? P0. This is going to be the integral from 0 to x of partial p, partial x dx. So all we have to do is to integrate this whole expression, which is a big expression. And I'm not going to do it here, and I'll just write the result. X dx. Now remember that h of x is known as a function of x. H of x is equal to h naught plus alpha x. So h is a known function of x, so you can actually integrate this expression. Now when you do this integral, which is this one is actually quite difficult to do, it's more tricky. You may want to you can do it directly like this with x, or you can do a change of variable. Where you change your x variable for h. Right? Instead of doing an integral from 0 to x, you do an integral from h equal to h0 to h1. So you change this integral from 0 to x dx as in from h equals 0 to h1 dh integral. You can do both. The equivalent is just that the one in h is easier to write because you already have this function here as a function of h. So it will be easier to integrate in h than to integrate in x. Right? I mean, this change of variable comes from here. H is equal to h naught plus alpha x. Right? So instead of doing an integral in x, you can do an integral in h. Is that clear? Yeah? It's technical detail, so it's not really interesting for fluid mechanics, but that's how it is. Okay, so when you do that, once you've done this integral, then you have p as a function of x. Right, so you have p as a function of x.
Sure,
yeah.
The 6 in there.
The where? Yeah.
6 u.
U? Yeah.
12 or
which one?
in the box, the dpdx, the partial t function.
So okay, I did these before. So in principle, I've checked all of that. So this is a minus 6 mu u divided by h squared, and this is a minus 12 mu q0 divided by h cubed. Did I do something wrong?
In the q above, there's u h.
Hold on. What did I do?
The last term in the q naught.
This term here.
Yeah.
Am I missing something here?
Yeah.
Oh yes. Am I? I'm missing a 1/2. Is that what I'm missing? Here I wrote 1/2. I have a 12. Yeah,
Yeah.
1/2. Yeah, you're right. There was a 1/2 here. See? Even when I've written everything before, I do mistakes when I copy. Okay, 1/2. So those are always details. Huh? This is always detail. Of course, the detail matter in the end because it's important. But you know, like of course, also in an exam, usually those you know you will not have those difficult integrals to do. Or if you do, then I will give you like the expression for the integral. Okay, so hold on. Where am I now? So now we know what the pressure distribution is. Right? We still have a little problem, and that is the fact that we have two more unknowns. You know, we want to know H naught. We don't know what H naught is, and in principle, this is the only thing we don't know. But here now we have a P0, and we have a Q0. Right? So it's something else we need to assume, and that's the following. So from our problem, from a physical problem, if I assume that I had P naught here, pressure 0 here, right? What is the pressure here? In that example. Huh? P0. Yeah? Okay? In all of our chambers, everything is repeated. You know, if I'm thinking about this, what's happening in that here, you know, in between my different grooves, everything is periodic. So I have P0 here. Then something happens here, the pressure increases, but then has to drop back to P0 here. And same here, increases, then has to drop back to P0 here. It's just repeated. I have all of these little things. I'm just looking at one chunk, but therefore I have to have periodic boundary conditions. So my pressure on one end needs to be the same as the pressure on the other end. Okay, so here this is P naught. And so when you do that, so if you add, once you have this expression for P, so we have P as a function of x is equal to la la la, and then you have P, when you add that P at x equals 0 is equal to P at x equals L is equal to P naught, then you can identify everything. You can identify Q0 as a function of P naught. Yeah? So this will give you, I invite you to do that Q naught is equal to minus U H1 H0 divided by H1 plus H0. So the periodicity determines Q naught. Right? And note that Q naught, of course, is still dependent on H naught. We still don't know what H naught is. Okay? Okay. And so at this point we are almost done. So we can write what the pressure is, and you'll find that the pressure is equal to, I'm just going to write it, 6 mu u. This is the result from the integral alpha. Remember that alpha is equal to h1 minus h naught divided by L times h1 minus h of x times h of x minus h naught divided by h of x squared times h1 plus h naught. That's the final expression for the pressure distribution underneath in our gap. Okay, now let's look. Is that going to be a large pressure? Yes. This here will always give roughly like h1 minus h naught. Right? This here, then we have an h cubed on the bottom. And this in particular, this is an h squared. Yeah? So h is small. So this is going to be a small number, so the pressure is going to be high. Same, alpha is also a small number. So here you have all of the ingredients that indicate that the pressure, which is going to be generated underneath the plate or in the gap, is going to be high. Right? You're dividing by small numbers. Now, we are only estimating here the overpressure compared to the pressure where the height is much larger in the reservoir. Now you can even think, thinking about this right here, if the pieces were thicker, if the pressure is if the height is significantly higher, then you can even think that the pressure in there will be close to the atmospheric pressure. Because here, the gap is in contact with this atmospheric pressure. Of course, things are rotating, so it's not exactly true, but you know, P naught, what exactly P naught is, you know, yeah, yeah. You can think of this as P atmospheric. Okay, so this is our pressure. Now, how do I get to the normal force? Because remember, this is what we started from. We want to know what the force is, which is pushing this plate up, which maintains this plate at a certain distance from the bottom plate. So what is that force? How do you get to that force? You integrate the pressure. Huh? So if you now compute integral from x equals 0 to L of the pressure x times the y direction y dx, I get to my normal force. Yeah? Now, can anyone give me a scaling for this normal force? If you had to, before you compute that, come up with a scaling for that, what would the scaling be for the normal force? Huh? How will you get to that? If actually, I should have done question number 1, scaling for this force. And how will you get to the scaling? Right, so the scale is going to be roughly a scale for the pressure underneath in the gap times L. That's roughly what the force is. Yeah. Do you have a scaling for the pressure if you have a lubrication film? Yes, right? We do. From this equation, actually we derive the scaling for the pressure. But the scaling for the pressure is here. You know, P divided by L is going to scale roughly like mu U divided by H squared. Right? So our pressure is going to scale with mu U divided by H times L divided by H. You know, L divided by H. This is also roughly what alpha is. Right? If your gap size is the same as your H1 minus H0, you know, roughly. So, but this is what you would expect for the normal force, the scaling for the typical normal force. So you would expect that your normal force scale with P, and P here we said is mu times U divided by H squared times L. Times another L, right? This is P, and then I have times L. Yeah. This is Fn. So if you compute the normal force, so I'll just write it down. The normal force is equal to here. You'll get 6. You exactly get 6 mu U divided by alpha squared times the log of H1 divided by H0 minus 2 H1 minus H0 divided by H1 plus H0. Now we know what H1 minus H0 is because this is what we grew, so we machined now, so we know. Now what would set H0? That would be an exam question. Eh? What's going to set H0? Yes, the mass of what is on top. Right? This is what we're going to set H0. I mean, this Fn is balancing this force upwards is balancing a certain mass. Right? Once you know the mass, you can determine H0. So just think of here. Once I'm moving, I have a certain velocity. What sets H0 now is the mass of what is on the top. Yeah? Okay. How, if the question was compute the tangential force, So the tangential force on the top, the friction force on the top rotating plate or the top flat plate, because you may want to know how slowly it's going to decay. What would you compute? The friction force on the top plate. What would that be? So integral, yeah, over x, over the top plate, from 0 to x of what? So you can write everything in tensorial form, no? But at this point I think you can sort of, you know which part of your stress tensor you're gonna find. I mean your stress tensor is still the same, huh? Your stress tensor is still minus pi for in a compressible flow plus 2 mu e. This is still what you have. But which term is going to be, which is the term which is going to stay? Huh? So, yeah, okay, 2 mu, yes, okay, yeah. Because you're on the top plate. You're on the top plate, so pressure is acting. I mean, of course, we have a slight slope, but in reality, just look at that. The slope is really, it's almost flat. So you can assume that the normal vector is just in the y direction. So indeed, you know, the component of the force in the y direction is going to come from pressure. Yeah. So if you're looking at tangential force, pressure is not going to give you a big component. Yeah. So what? Huh? The shear stress. Yeah. So what is that going to be? So this is very important that you get every detail of this right, because you know oftentimes in an exam, that's the first thing you write, and it's worth probably more than half the points. You know, if you write the right integral, if you're computing the right quantity, if I see you computing the right quantity, then I'm happy. Right? So it's the you know, everything is in the detail here. So you're integrating between 0 and L, right? So what are you integrating? Huh? Times the, yeah. So I would still not be entirely happy with that. There's the area. Yeah, in that case it's 2d, so we have a dx. But that would still not be enough. Yeah? Huh? Sorry? So you mean on x? You mean this? Yes, but you know here I'm assuming the f of t is really f, the total force dotted on x. Right, so this is a scalar, yeah? So I would still not be entirely satisfied with that. Why? Huh? No, the divided by what? You don't have to divide anything. No, it has to do with really which quantity exactly you're estimating. I think you have it. At the top surface. So you would write what here? Yeah, so it would be perfect if you actually wrote at y is equal to h and you made it clear that h is a function of x. Huh? Yeah, that would be the right answer. This is essentially t dot n projected on t, but you're expressing it at the right point. If you just write du dy, yeah, this is du dy, it's a component of your tensor, and your tensor is defined everywhere, but you want to know the force on the top plate, so you have to say like where you're expressing this stress, and that stress is expressed on the top plate. Yeah. So when you compute that, of course you know what du is, you know the expression of u. It was actually a polynomial in y, so you can compute partial u or partial y, so you can integrate that. So again, this is work on your side, you have to do it yourself. Here it's the same, you have to compute this integral. And in the end you get let me write it here, equals 2 mu u alpha. This is just for you so that you know what the answer is when you try it at home. Plus, I think a log of h1 divided by h naught. Okay, you can verify that indeed f of t is much more than f of n. If I had asked you for a scaling for f of t, what scaling would you have written? Ft would scale with what? If that was the first question, before we did any analysis, what would be a scaling for the tangential force? And here note that everything is per unit length in the board, right? Because it's 2D, always our forces are going to be force per unit length. There is a unit length in the board. Right? So what would be a scaling for Ft? If you can write this expression, then you can write it. So you're integrating over a length scale L, over the entire length of this little pad here, a shear stress. What is the scaling for the shear stress? Mu times U divided by H. Yeah? This is the scaling for your shear stress. And you can actually already find, just from this scaling and from that scaling, right, you have a factor alpha between the two. You see, they look almost the same, but f of n has a 1 over alpha. And alpha is a small number. So just from here, just from the scaling analysis, you see that f of n is going to be much, much larger. The normal force here is going to be much larger than the tangential force. And this is what you have here. If you look at this now, you can imagine that the alpha is really, really small. You don't even see the group. So the difference between the thickness at the smallest point of where the gap is small and where the gap is big is really small. So this alpha is extremely small. This is why you have a big normal force. Okay. So we're done with this problem. The other one is going to be shorter, so the other one we'll go quicker over. Yeah?
How do you do that?